Hi, everyone. Hey, let's look at more substitution and elimination reactions. Last time we saw the SN2 reaction. So we are here in Key Concepts Unit 3, Part 3. And doesn't hurt to look at this first paragraph again. There are four mechanisms that alkyl halides can do. SN2, SN1, E1, and E2. And that can lead to a whole bunch of different reagents and different products. So the key is to learn the mechanisms and the four factors that help you decide which of the four, hopefully there's just one, that's going to operate the fastest. The fastest mechanism is going to determine the major products. Cool. All right, so last time we saw SN2. Let's quickly just jot down the mechanism. So this is the reaction we saw last time. How do we characterize this as SN2? Well, first start with the four factors. The alkyl halide is secondary. So, SN2 doesn't like crowding, so primary works best. Tertiary doesn't work at all. Secondary can still work. Second factor is the nucleophile. And we have a little slogan for that. Good nucleophiles are strong bases and SN2, sulfur and nitrogen. So here's sulfur. And so that's going to be a good nucleophile. Sodium is positive. It's a spectator ion. It just helps us identify the anion. Okay, and that is a good nucleophile. And so, you know what? We'll see in today's video, we're going to do elimination reactions where the compound with the lone pair may not be a nucleophile, but instead it could be a base. So I'll just say right now that sodium hydroxide is a stronger base than sulfur with a negative charge because as you go down the periodic table, base strength decreases because the atom becomes larger, the negative charge spreads out over the atom, and it's more stable. And stable is the opposite of reactive. Okay, so sulfur is a great nucleophile, but not that strong of a base. Strong bases do the elimination reactions, E2. Anyways, so we're kind of narrowing it down. This is looking more like SN2 because it's a good nucleophile. Third factor is the leaving group. Doesn't help us decide, just helps speed up the reaction. Iodide and tosylate work the best, then bromide, then chloride. So this goes medium fast. Bromide is a good leaving group and all four mechanisms, so it doesn't help us decide which mechanisms work. Lastly is a solvent. So let's add a little DMSO, one of the polar aprotic solvents. Remember, polar solvents dissolve other polar compounds. Like dissolves like. Aprotic means no hydrogen bonding among itself, meaning DMSO doesn't hydrogen bond to DMSO. What's DMSO? We can draw it over here up the side. It's two methyls attached to sulfur and double bonded oxygen. That's a solvent. Doesn't gonna turn, these atoms will not show up in the product. All right, let's do the mechanism. SN2, nice and quick. Two arrows, one step. Lone pair swoops in and attacks the carbon directly and kicks out the bromine, kicks out the leaving group. Where the halide used to be, that's where the atom with the lone pair connects. For SN2, we get inversion of stereochemistry, meaning if you start on a wedge bond, you end up on dash. If you start on dash bonds, away bonds, then you get the wedge bond. And if you don't specify it or the molecule's not chiral, then just leave a regular bond. Inversion of configuration is the word, the phrase rather, that switches wedge to dash. Okay, SN2, we're going to contrast SN1 before we draw up the mechanism, let's just take a look at the definition of Sn1. S stands for substitution. N is nucleophilic reagent. So again, somebody with the lone pairs is going to attack the carbon. It is unimolecular. So the 2 of Sn2 means bimolecular. That means bimolecular, you might remember from general chemistry, means that bimolecular, there's 2 molecules in the slowest step. The slowest step is the rate determining step. Well, for Sn2, there's only 1 step. It's where the nucleophile attacks the halide. And yeah, there's 1 molecule attacking a second. There's 2 molecules in this slow step. And the faster these collide, the faster the Sn2 reaction occurs. But in Sn1, there's only 1 molecule reacting in the slow step. So let's see it. Let's do this example. I'm going to change the alkyl halide. It's not going to be secondary. The bromine is now on a tertiary carbon. Excuse me. Tertiary, how's that work with a Sn2 reaction? Doesn't. That's too crowded. Okay, so that's why I changed the structure, so I don't get an Sn2 reaction. Tertiary alkyl halides are too crowded for Sn2. Sn2 is way too slow. Someone else is going to win the race. I also don't want to use a good nucleophile, it turns out. So I'm going to change my nucleophile to an alcohol. And I'm not specifying a solvent. Or you can assume that maybe there's excess of this alcohol. This is methanol. That actually is a decent solvent. Is it polar, aprotic? Well, the alcohol group's definitely polar. Oxygen is more electronegative than hydrogen. So there's slight positive charges. This is a polar molecule. But it can hydrogen bond. This is a protic solvent. Okay, the Sn2 reaction takes place. We'll verify that by going over the 4 factors in just a few minutes. Here is the mechanism. The slow step happens first. Just kind of warm up this reaction, or it just sits, and as the molecules bump around in solution, this bromine just breaks away. 1 molecule self-reacts. And after it breaks away, this carbon that I'm highlighting as a dot will then only have 3 bonds, and it becomes a carbocation. Wait, you're saying, what about the dash bond to the methyl group? Well, what's the hybridization of a carbocation? Something that only has 3 bonds. 3 bonds means you need an S, a P, and a P. It's sp2. And the shape of sp2 is trigonal planar, flat, triangle, flat. Where's the wedge bond? It's gone. It's been wiped clean because, oh, the wedge or the dash. This carbon is now flat. None of these bonds are in or out of the plane of the paper or the screen. It's flat, sp2. Okay, now bring in your reagent, the nucleophile in a substitution reaction. So it attacks the carbon. Just like this lone pair attacked the carbon, but in Sn1 it happens in the 2nd step. And the oxygen just connects and gives carbon its 4th bond, yay. And now, how does the oxygen attach? By a wedge or a dash? The answer is yes. It can do both, right? This is flat, the carbocation, so the alcohol might have been behind the molecule when it attacked, or the alcohol could be in front of it and attack. 50-50 shot, on average. There's an exception to that coming up in just a second. So you get a mixture. So I'm not going to use dash or wedge bonds. I'm just going to use regular bonds. And that means, is this a chirality center? Yeah, it is. It's got a methyl, it's got a propyl, it's got an ethyl, and it has an ether that has a hydrogen on it. There's 4 different groups. That's a chirality center. But it's a racemic mixture where we get both enantiomers. So the shortcut is don't draw a dash, a wedge, just draw regular bonds, and it represents a mixture of both. Cool. One last step here to get to the final product. Bring in another reagent, another nucleophile, but this time it's going to act as a base. Lone pair is going to pick off that hydrogen, and we end up with our final product, an ether. If you want to write the methyl group on the left-hand side, you can. When you're drawing it, you decide how you want to draw it. And then the product of this other methanol molecule grabbing a hydrogen is right there. There's the mechanism. Cool. So we get our racemic mixture. That usually results in an Sn2. So in the laboratory, this is evidence of an Sn1. You can do a reaction that you've never seen before. And you want to say, is it Sn1 or Sn2? Well, if you start with a chiral molecule and you end up with a chiral molecule, you don't get a mixture of both enantiomers, that's evidence for Sn2. If you start with a chiral molecule, but you do get both enantiomers, that's evidence for Sn1. And it turns out you don't get a perfect 50-50 ratio. I would have thought so, right? This is flat, so why not come from the backside or the front side methanol? Wouldn't that be 50-50? Well, it turns out that the bromine leaves on the forward side. It's on a wedge bond. And sometimes it hangs out there because opposites attract. It doesn't attract strong enough to reattach, although I suppose it could. That would be an equilibrium reaction. Well, what you get something is ion pairing. That so this is the bromine here, and this is the carbon, and the bromine bond breaks. Bromine, the carbon bond breaks, and this is the Br minus, and it's kind of hanging out there. So then your nucleophile is like, hey, get out of the way, and the bromine's like, no. So the alcohol says, well, now attack from this side. This is the nucleophile. That is your alcohol in Sn1. Whereas sometimes the carbocation exists for a little while, the bromine gets knocked away by the solvent, and then you have a clean shot at either side, and you get a mixture. But every once in a while, that halide hangs out there a little too long. The nucleophile is a little too impatient, or rather the carbocation is one that's unstable. It's like, hey, come over here, oxygen. And the oxygen will do, and this will be easier to attack from this side if the bromine is blocking the other side. Cool. We get a racemic mixture, or you could say the product was racemized, or you achieved racemization. I know, chemistry, all these crazy terms. But if you see a racemic mixture, racemization, racemized product, that's evidence of Sn1. Okay, what else we got here? Oh, Sn1 stands for unimolecular, one molecule in the rate determining step. So here's the rate law for unimolecular. You have one molecule determining the rate. And the one molecule is the alkyl halide. We're waiting for the halide to leave and form the carbocation. What does that mean? Well, if this is your rate law and you double the concentration of alkyl halide, you double the rate. Reaction rate doubles if the concentration of alkyl halide doubles. What if we increase the concentration of the methanol or the nucleophile? Well, there's no nucleophile in the rate law. There's no effect. So change the concentration of nucleophile, you will not see a rate increase. Try that in the lab. If you observe that, hey, that's also evidence of Sn1. Sn2, the 2 says the nucleophile and the alkyl halide affect the rate. So if you add more nucleophile and the rate changes, goes up, that's evidence for Sn2. Okay, 4 factors. Now, these factors you got to look at to help you decide who is going to win the race and determine the major product, Sn1, Sn2, and later in the video, E1 and E2. So for Sn1, The four factors are the same four factors we saw for Sn2 reactions. Sn2, we've looked at alkyl halide, the nucleophile, the leaving group, and the solvent, four things. So let's look at them again in the same order from the point of view of Sn1. Okay, in the Sn1 reaction, the slow step is forming the carbocation. So how can the alkyl halide affect the rate of carbocation formation? Well, not too long ago, we talked about carbocation and radical stability. We said that at the heart of it, tertiary carbocations and radicals were more stable than secondary. And secondary carbocations and secondary radicals, more stable than primary. Primary is more stable than methyl radicals and carbocations. And then we added to the list. We said, you know what? Resonance helps stabilize things. So if you have an allylic radical or a benzylic, meaning that one carbon away from a pi bond, you have a radical, or you have a carbocation, one carbon away, you get resonance. Oh, let's make sure it's benzylic, a benzene ring. So there's 3 pi bonds in this hexagon. Allylic, same pattern. You have your pi bond, and one carbon away, there's a carbocation or a radical. And that enjoys resonance stabilization. Stabilization, it's more stable. There's some argument whether tertiary is actually more stable than allylic or allylic's more stable. If the allylic carbon is not primary, it's secondary or tertiary, then it tends to be more stable. Let's just leave the ordering this way. Benzylic and allylic, on the exam, I'm expecting them to be more stable than tertiary. That's the answer I'm looking for. And then pi bonds are affected over here on the other end. If you attach a positive charge to the carbon that's double bonded, sorry, that should be a radical. That is really bad. Those are vinyl carbocations, vinyl radicals. Or if you have an aryl carbocation, the carbon is on the sp, hybridized carbon. These are super unstable. I'll just say very unstable. Nature just says, nope, we're not even going there. They're not going to react. They're too hard to make. Right, so the bottom line is that's a pattern we had to remember. Now we apply it. In Sn1, you make a stable carbocation. So tertiary is going to do Sn1 very well. So are the allylic and benzylic halides. So if you have a benzylic halide, that can easily form the radical, the carbocation. Sn1 makes carbocations. Bromine can leave, and then you get the plus charge on the carbon next to a benzene ring. Allylic works really well. And bromine's my favorite halide, but chlorine, tosylate, iodide, they all work here too. And then tertiary, those are going to work really well for Sn1. Cool. Primary though, that's not very crowded, not very stable for carbocations. So Sn2 favors primary alkyl halides, but Sn1, no. The carbocation is not stable. It's hard to form. It's too slow. Someone else wins. Cool. Enough said about the first factor, the alkyl halide. Okay, second factor, the nucleophile. It's not in the rate law, so it has no effect. Okay, the one thing you have to look out for that will become evident as we go through this video is that if your nucleophile is basic, then it might do an elimination reaction. Well, yeah. So even though adding the nucleophile, increasing the concentration won't speed up Sn1. If you choose a nucleophile that's also a base, now the base reactions, E1 or E2, those elimination reactions, might might beat out the Sn1 reaction. So let's just be a little careful about that. All right, that's second factor. The third one's a leaving group. We're going to keep referring to this because it's important for ranking alkyl halides in terms of how quickly they react once you choose a mechanism. But sadly, knowing the leaving group does not help you choose between Sn2, Sn1, E1, or E2. Yeah, it's just that if you have an iodide, so if you have, let's say, a tertiary iodide, and then you're reacting it versus a tertiary bromide, the tertiary iodide goes faster because I- iodide is actually more stable than bromide. Iodide is a larger atom, negative charge spread out over a bigger surface area. Iodide, bigger atom, bigger ion, that's more stable, easier to form. Chloride, it's smaller than bromide, it's less stable. It's slower to form because it's less stable, meaning it'll be a slower reaction. And then the tosylate is faster. You can write OTS, you can write it this way, whatever you want to do. You can also add an O in there. You can draw it. So draw a benzene ring, methyl group on one side, sulfur with a pair of double bonded oxygens, and an O minus. So this O minus is that O minus. And then we're going to add one more. If your reaction is Sn1, and we'll see in a little bit E1, turns out that, remember up here we said the nucleophile should not be basic? In fact, it's okay if it's acidic. If it's acidic, then you can get alcohols to react, and in which case, your leaving group is a water molecule. Let's show an example of that. Actually, I think we may have already seen it, but we'll do it again. So most of the time, we talk about Sn2, Sn1, E1, E2, we're talking about alkyl halides, right? So the halide on our alkane. But now with Sn1 and E1, we'll see in a bit, you can get alcohols to react. So how does that work? Well, the alcohol is a weak base because oxygen has a lone pair. Lewis bases have lone pairs, lone pair donors. HCl is like, here's an H plus, who wants it? And oxygen says, oh, I'll take it. I'm gonna write the H on the other side. Remember, whoever draws it gets to decide how to draw it. And now there's a second H there. And oxygen makes three bonds. It was making two. Picks up an H, making three now. 3 bonds means it's positively charged. And there's the water molecule that can now leave in the Sn1 mechanism. So it's going to leave. Water comes out nice and stable. And then what's left behind? 4 carbons, where the center carbon is only making 3 bonds. It's a carbocation. When the HCl molecule attacked, I forgot to write there was a Cl minus. The Cl minus is still there. Cl minus can then attack the carbocation and attach right there. And this is a good way to make alkyl halides from alcohols. So if we go back a couple videos ago, we did see this reaction. We talked about how you can change alcohols into halides with HCl or HBr. You can also use PBr3, SOCl2, phosphorus tribromide, thionyl chloride. Okay, so we have seen this reaction before. Here's the mechanism. We probably did it before too, but this part of the mechanism is actually the Sn1 mechanism. If you want to know what this step is, it's simply an acid-base step. Cool. Okay, and so in this way, if you're using an acid, this is not a basic nucleophile, it's an acid. So we're not going to get E1 or E2. Well, yeah, we're not going to get E1 or E2. That's just not a base. Even Cl minus is not a base. Yeah, so that's why we don't get any. If you look at the rest of the video and come back and watch this again, you might say, wait, this is Sn1. Shouldn't we also get E1? The answer is no, because chloride is not a base. Do you remember how chloride ions do not change the pH of water? They're not basic. So can't be a base. No E1. Okay, last factor is a solvent. Well, it turns out carbocations form more easily in a protic solvent, in a polar solvent. They can also form in aprotic solvents too. So it turns out the solvent really does not affect the rate. So you can use anything. However, remember it's a race between Sn2, E1, E2, and then the Sn1. Why don't we slow down Sn2 by avoiding aprotic solvents? And that's the choice here. If you don't want Sn2, don't choose the polar aprotic solvents. And what were they? We have to memorize these for, I started writing it, sorry, for Sn2 solvents, for Sn2, get my English going correctly, DMSO, DMF, 2 DMs, yeah. And then we have acetone and acetonitrile, so 2 A's. We should also know the structures. These are the polar aprotic solvents, the ones that can't hydrogen bond to each other. If you use one of those solvents, then Sn2 might go faster than Sn1. And if you want Sn1, don't use these solvents that are meant for Sn2. Use the polar protic solvents, protic solvent that can hydrogen bond. And those are water, alcohol, ammonia, right? It has an NH bond, and the amines also have NH bonds. Alcohols and water have an OH bond. You need that for hydrogen bonding. Finally, we scroll up to the top of the page here. Not top of the page, but when we did our example of Sn1, we decided to use methanol by itself. It's also used as a solvent. And the solvent kind of cut the halide away. It lysed it, it cut it. Sometimes the Sn1 reaction can be called the Solvolysis reaction because the solvent actually is reacting. So the methanol molecule served as a solvent to dissolve everything. And after the alkyl halide created the carbocation, the solvent attacked it. Now it's technically a reagent, not a solvent. But use an excess of the methanol. So it does both. It serves the role of solvent and the nucleophile. So anyways, something to be aware of. You see that in the homework question. It might say, hey, in the following Solvolysis reaction, ding, 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 Sn1. Ooh, we're done with Sn1, I think. Let's double check. Yep. All right. So we've seen Sn2 and now Sn1. Those are substitution reactions. But alkyl halides can also do elimination reactions. So let's look at E2. Double check my notes, make sure I didn't forget something. Solvolysis we got. Yep, we're good. All right, so as an example, let's pick a tertiary bromide. We'll explain that in a minute in the four factors. And let's choose, how about hydroxide ion in water? I chose water because it's a protic solvent and I want to avoid Sn2. Remember, the Sn2 solvents, help the Sn2 reaction go faster, but I'm trying to do E2. Okay, and then between these two molecules, which one's more reactive? Well, sodium hydroxide is a strong base, water is a weak base. Oxygen is negative up here as in sodium hydroxide, and the oxygen in water is neutral. Okay, so hopefully you picked the hydroxide ion to be your true reagent, and the water is now the solvent. It's weaker, it's less reactive. Solvents aren't supposed to react. We're going to do E2. So E, elimination, they make alkenes and alkynes. They make pi bonds. And usually the pi bond begins, the double or the triple bond begins where the halide's attached. The definition, we should have went over that. E2, E stands for elimination. So kick out some atoms, don't add new ones. The 2 stands for bimolecular, just like in Sn2, second order kinetics, 2 molecules, bimolecular in the rate determining step. And that's the definition. Let's see the mechanism. Like Sn2, nice and quick. Sn2 has 2 arrows, E2 has 3. So start on the lone pair of your base and go after, hey base, you want an H+? Well, let me see if I can find one. Here's the idea. We're going to make a double bond through elimination. Bromine's going to leave, free up room to have the beginning of a double bond on this carbon. Right? This carbon's making 4 single bonds. If it wants a double bond, it needs to kick out a group so it can double up a bond to one of the carbons. The other carbon at the other end of that double bond, well, all 3 of these are methyls. They have 3 hydrogens. We're going to have to eject one of the hydrogens. There's my H+. So hydroxide ion is going to grab the H as H+. What physically is H+? A naked proton, right? H, hydrogen, is the element with 1 proton, 1 electron, but H+ doesn't have that electron. It's simply a proton. So hydroxide ion rips away the H+. These electrons are left behind in carbon, but they collapse to form the double bond. And as these 2 electrons formed a double bond, the pi bond, this carbon says, whoa, I can't make 5 bonds. So if I'm making another bond up here to this carbon, the bromine that's more electronegative, tugging on these electrons, will take full control and rip them away from the carbon. And that's our mechanism. 3 arrows, double bond up here, just because I picked off the hydrogen up there. And then what became of hydroxide ion? It picked up an H. So the O now has 2 H's. That's water. They put the Na next to the water? No. Na is positive, water is neutral. No reason to stay there. The bromide, however, came off as Br minus. So that's going to form an ionic bond. This is the mechanism, so you do have to show our byproducts. If we're just predicting the products, you would not have to list the atoms that do not contain carbon. Oh, are there other double bonds? Well, you might say, what about this hydrogen? So pull off the hydrogen, make the pi bond, kick out the halide, and then our double bond goes this way. We could also attack from the other side, and the double bond would have gone that way. If you want to draw all 3 of these, draw all the arrows, all that good stuff, full credit, but you can take a shortcut and realize, wait, what's the name of this? If this is carbon 1, the 2, the 3, so get to the double bond as fast as you can, there's a methyl group on 2. And then we do the same thing here, 1 to 2 to 3, there's a methyl group on 2. This is the same molecule, these are the same. Starting the double bond, 1, 2, 3. Hey, there's a methyl on 2. All 3 of them are identical. So you only have to draw the first one because these 2 are the exact same molecule. So you only have to draw this, get full credit on my exam. Nice. So back in Key Concept Unit 2, Part 2, we talked about how nature prefers to make alkenes that are very stable, where the more stable alkene has more groups on it. The Russian scientist Zaitsel was the one that first formulate that idea. So we honor him, call this Zaitsel's rule. I know we have Mykovnikov's rule, the rich gets richer. Zaitsel's rule says, hey, which double bond alkene is preferred? And we might have to circle that in some of our exams. But right now, we only made one alkene. That is the major product. Okay, what else do we need to know about E2? Well, the 2 stands for bimolecular, second order kinetics. So 2 molecules in our rate law, bimolecular. 1, 2, bimolecular, yep. If you increase the base concentration, add more hydroxide ion, the rate goes up. Add more alkyl halide, hey, that's in the rate law too, rate goes up. If you double both of those, the rate will quadruple, a factor of 4. Cool. Let's take another look at Zaitsel's rule. So what we have here, we say circle the major product. And I'll put an S in parentheses because I don't know whether there's one major product or if there's several that are tied. So it could be more than one major products. Find out. All right, first we have to say, what's this reaction going to do? Well, 4 factors. Alkyl halide, it's secondary, darn it. Primary halides like to do Sn2. Tertiary like to do Sn1. We haven't talked about the factors yet. It's coming up soon for E1 and E2. But right now, no decision based on alkyl halide. Look at the reagents. For Sn1, we said you don't want a strong base because it could do an elimination reaction. Hey, negative oxygen here next to sodium, positive. This oxygen is a strong base, just like O minus. If I draw it this way, that's NaOH. So instead of an ethyl group, put a hydrogen there, and that is sodium hydroxide. This is a strong base, just like sodium hydroxide is a strong base. Wait, you don't want that for Sn1. This won't do Sn1. But for Sn2, we said nucleophiles, good nucleophiles are strong bases and Sn2. Strong base is a good nucleophile. Hey, this is a good nucleophile for Sn2. Yeah, but what about the solvent? An OH group can hydrogen bond. This is a protic solvent. That's going to slow down the Sn2. So this doesn't do Sn1 and it doesn't do Sn2. It's going to be E2 or E1. We haven't talked about E1 yet, so I'll just tell you it's E2, which is why it's here in the E2 section. Ha. Okay, E2, do your thing. 3 arrows, 1 step. Base, go grab a hydrogen to make a pi bond. So how does that work? This halide is going to leave with the 3rd arrow. So right here, come on, right here, this 3rd arrow, the halide leaves. 1 carbon away will be the hydrogen that gets removed by the base. And in between where the hydrogen and the halide where they are, is where the double bond is formed. Another way to think about it, wherever the halide is, that begins your double bond. Okay, so this begins my double bond. It could go to the left if this hydrogen is removed, and it could go, the double bond could go to the right if this hydrogen is removed. We have to drop both products. So let me squeeze it in down here. I'll put this here. I'm going to leave off the sodium. I'm just redrawing the molecule, but remember, sodium is a spectator ion. The oxygen with negative charge is going to remove that H. these electrons form the double bond, the pi bond, and the bromine bond breaks away. And then we get a double bond right here where the hydrogen and the halide used to be. Make sure you erase the line to the bromine. Some students keep that line there and accidentally add another carbon. Yeah, don't do that. The bromine left. And this is a mechanism, so you have to show the other products. The oxygen received this hydrogen. Bromine matches up with a sodium. I think that's it for this molecule. But the base can also remove that hydrogen, meaning these electrons go here to make the bond that position. Bromine, you leave again. You're the leaving group. And the double bond goes here. Oxygen gets a hydrogen. Sodium and bromine pair up ionically. Those are all our products. And then we have to consider any cis strands. This one, there's a pair of methyls. If you switch them, put this methyl up there, that methyl down there, it's the same molecule. This one, however, is trans. So we also get the cis. Now on the exam, I'll let you skip the mechanism to the cis. It's going to look like this. Let's put it over here. You have to get into a new shape. Remember back in Unit 1, draw Newman projections. Single bonds are free to spin. So before the reaction even gets started, this molecule is in equilibrium with a different shape. You can just spin this group here. So the molecule might be in this shape. Then you can add the base. And there's a hydrogen here that can be removed. To make the double bond there, kick out the halide, and then the double bond is created here and locks the molecule into that shape. And that's supposed to be this one. Plus the OH plus the NABR. Okay, so I drew all the products. There are 3 of them. Now we're supposed to circle the major product. And the nice little trick, will this work? If we circle this, I cut 3 bonds. If I circle this, that's 2 bonds. Sorry, I didn't change the color. That was silly. I had the chance to. This dye substituted. I think I'm stuck with it. Anyway, this one had 3. This is the major product. So circle that. Be a little careful. I actually circled everything, showing my work. So you might want to clarify it on the exam. Say, Dennis, I didn't mean to circle everything. So you might want to just say this one is the major one. And that's how you do it. All right, there's the mechanism, circling the major product. And we use Zaitsel's rule to predict the major product. It's the alkene with the most groups, 3 groups hanging off of it. All right, 4 factors. Let's clear the screen of the notation here. There we go. Okay, 4 factors: alkyl halide, nucleophile. Well, in E2 and E1, they're not nucleophiles, they are bases. So our 4 factors will be alkyl halide, the base, not the nucleophile, then the leaving group, then the solvent. Cool. All right, look at the alkyl halide first. Well, for E2, it doesn't really matter. Why not? Well, because Let's look at tertiary halide. Let's look at a secondary halide, and let's look at a primary halide. We're going to have a base doing E2. Where's the base attack? The primary, the secondary, or the tertiary carbon? None of them. It goes after an adjacent hydrogen. What degree are those hydrogens? Well, this one's primary. This one's primary. That one's secondary. And really, hydrogen's pretty tiny. It's not that crowded at all. This base has no trouble picking off this one, or picking off that one, or picking off that one. So it doesn't matter what the alkyl halide degree is, how crowded it is about that carbon, it doesn't matter. The base goes after the adjacent carbon's hydrogen. So yeah, that has no effect. That stinks. So when we're trying to determine Sn2, primary is the best. And it's like, ooh, if it's primary, that's leaning toward Sn2. Sn1, stable carbocations prefer tertiary alkyl halides. Ooh, so if it's tertiary, that favors Sn1, kind of eliminates Sn2. But if you're saying, well, is it E2? Your degree of the alkyl halide can't help you. They all work equally well. All right, but E stands for elimination. You need a base to eliminate a hydrogen. So more base, faster reaction. You need a strong base to make it work. If you have a weak one, then it doesn't do E2. It's probably going to do, more likely to do E1. So you can look at the base strength. Yeah, water is a weak base, right? So that can't do E2. You need a strong base. Okay, so that is helpful. So if you see that the only reagent is water, it's like, well, that's not going to be E2. That's not a strong base. Cool. Here we go again with the leaving group. It affects all of them, equally. It doesn't help you decide which mechanism works. Just more, the better leaving group makes for a faster reaction. Iodide and, tosylate's the winner. I would put water here, but water is only a leaving group under acidic conditions, and E2 requires a strong base. So water cannot be a leaving group for E2. Tosylate's your best leaving group if it's doing an E2 reaction. Iodide works really well too. Bromide's decent. Chloride, it works okay. But chloride is like, okay for all four of them. Using chloride can't help you decide which one of those are going to work. Solvent. Okay, this is similar to Sn1. The E2 mechanism, all the polar solvents work, whether they're protic or aprotic. You must use a polar solvent though, because you're using a strong base. Strong bases are charged, they're ionic. So you need a polar solvent, like dissolves like, to make them dissolve. If you use an aprotic solvent, that works. You will use a protic solvent, that works. But if we're intending to make an E2 reaction, don't choose a aprotic solvent. Don't choose one of the Sn2 solvents, because that can help speed up the Sn2. And maybe Sn2 will go faster and win and determine the major products. So if you're trying to do E2, choose a protic solvent, just so you can slow down Sn2. Right? The fastest mechanism determines the major product. Okay, so keep the aprotic solvents with Sn2. If you want Sn2 to win, then use DMSO, DMF, acetone, or acetonitrile. And if you don't want Sn2, avoid those solvents. Cool. There are times when someone will go ahead and use the aprotic solvent, in which case E2 and Sn2 can probably compete and be tied, and you have to give products for both. Sadly, there's also time when the solvent is omitted. You're not told which solvent's being used. And remember, SN2 nucleophiles? Good nucleophiles are strong bases in SN2, sulfur nitrogen. So the good nucleophiles are strong bases. E2 needs a strong base. Oftentimes E2 and SN2 compete, and it's the solvent that can help decide who wins. If it's one of the aprotic ones, SN2 wins. The alkyl halide, though, can help you too. If the alkyl halide is tertiary, then SN2 is too slow, and E2 will win. Cool. All right, what do I got down here? Oh, there's no solvent. So if I'm trying to predict the outcome of this reaction, look at the 4 factors. This is primary. SN2 is good. Sn1 is bad. Primary halides make primary carbocations. Sn2 is not going to work. E2 good because primary, secondary, and tertiary halides work well with E2. Okay, so look at alkyl halide, we narrowed down the SN2 or E2. How about the nucleophile or base? Well, oxygen is negative. That makes it a strong base. No resonance here, I should say. If you have the acetate ion, oxygen is negative there, but it's also involved in resonance. This is a weak base. Maybe you remember that from doing your ice tables back in Gen Chem. There's the acetate ion. It's a weak conjugate base of the weak acid, acetic acid. A better explanation is that there's a pi bond next to a charge and it can do resonance. Resonance stabilizes. If it's stable, it's not that reactive. Yeah, that's why it's a weak base. Thankfully, this doesn't have a pi bond next door. It's a strong base with that negative oxygen because there's no resonance. Okay, strong base. Strong bases are good nucleophiles. So this thing can do SN2. It can also do E2. All right, leaving group chlorine doesn't work very well for both. Doesn't help decide between SN2 and E2. Last thing is a solvent, and none's given. So we have to list both SN2 and E2 products. It doesn't have a question here, so I don't know if I'm supposed to give the mechanism or the product, so I'll just decide draw products. That'll be the question. Okay, so SN2, the oxygen attaches to the carbon where the halide is and substitutes for it. SN2, S stands for substitute. So wherever the halide is, that's where the oxygen attached. And oxygen, you're going to keep sodium or you're going to keep the methyl? Oxygen, the carbon is a covalent bond. That's stronger than oxygen sodium ionic bond. Covalent bonds are stronger than ionic bonds, right? Ionic bonds separate in water, they dissolve. Cations separate from anions, not the covalent bond. So there's the product from SN2. And then we can get a product from E2. Sometimes the O minus hits a carbon directly and substitutes. Other times it goes over here and grabs this hydrogen and makes a double bond through elimination. So you make a double bond beginning where the halide is to the other carbon. Any sister trans isomers? Nope. We're done. Nice. That's E2. Okay, we went over the 4 factors: alkyl halide, base or nucleophile, leaving group, and solvent. There's 2 more, I don't call them factors, 2 more properties, 2 more details about E2. This is specific only to E2. So E2 is the one that in the rate determining step, where's the rate mechanism? Now that's pretty messy. Let's look at this one. This is a little less messy. Rate determining step, the base removes this hydrogen. Deuterium is also hydrogen, but deuterium weighs twice as much, right? Normal hydrogen, protium, does not have a neutron in it. It only has a proton. Deuterium has a proton, making it hydrogen, but it also has a neutron. Neutrons weigh as much as a proton. So deuterium weighs twice as much as hydrogen, with twice the weight, twice the inertia. There's also some quantum effect happening that the covalent bond's a little bit stronger. It's harder to remove the deuterium atom than hydrogen. It slows down the reaction. It's slow because the slowest step involves pulling off the hydrogen, whether it's a normal hydrogen or a deuterium atom. So for E2, there's something called the deuterium isotope effect, that if you have deuterium in place that's being removed by the base, the reaction slows down up to 7 times slower. So you can measure the rate in the lab. Remember doing kinetics back in Gen Chem, measuring rates of reactions? So you can actually measure the rate. And if you detect a rate decrease when you use deuterium, that's evidence that an E2 reaction is happening. That's what's here in bold. So this is how it might occur in the lab. You could start off with this molecule, add base and water. Water is a protic solvent, so no Sn2. Strong base is a good nucleophile, but the protic solvent is going to shut down the Sn2. So the strong base, even though it's a good nucleophile, with the protic solvent, it's only going to be a base. Removes the adjacent hydrogen to the halide, makes a double bond. So if you want to draw the product, you can. That's not the main point. The main point is the bromine. What are you still doing there? Sorry, leaving group. Hydrogen is there now. One of these hydrogens are over there. Now we get the, and the water is formed when sodium hydroxide removes this H, and then the Na pairs up with the bromine. There we go. Normal hydrogen, remove one of these H's. Now the base has to go after deuterium to create the E2 mechanism, E2 reaction. And this deuterium is held on a little more tightly. It weighs twice as much, takes a little more effort. It's a slower reaction to this product. Deuterium is hydrogen, so that's why it's reacting the same way. It's just twice as heavy. Hydroxide ion added a D, so you might write DOH. I'm just thinking of Homer Simpson. No. Dad jokes, sorry. And it's kind of messy, so there's a big dope right there for that too. Main point is, in the lab, if you time these reactions, measure the rates of reaction, this one's much slower, all because of there is a deuterium 1 carbon away from the halide. And that's great evidence that says, hey, we have an E2 reaction happening. That's one detail. So if you see a deuterium isotope effect, E2. The other one is that all 3 arrows happen simultaneously. The deuterium atom bond is broken, the pi bond is made, the bromine bond is broken. So what is a pi bond? It's 2 p orbitals lined up and overlapping. In order to make the pi bond, you need to get those p orbitals lined up in advance. In other words, these electrons have to be in an orbital that is going to become the p orbital. These electrons have to be in the location that's going to become the p orbital, so that when the electrons go here, the p orbitals can sideways overlap and make the pi bond. An easier way to say that is that in order for E2 to work, the deuterium carbon bond and this bromine carbon bond have to be in the same plane. They have to be lined up. The scientific word for that is that all four atoms, the CC halide, that was a bromine, the hydrogen, this bond, that bond, and this bond technically, all have to be in the same plane. So it's called periplanar geometry. So the molecule, if this is a single bond, which it will be, well, there's an exception to that. It may be a single bond. It could free the spin. The E2 reaction needs to wait for the molecule to get into this shape in order for it to work. Now, you can also be flat in this shape, right? This still can be flat and periplanar. So this is technically called the Sn periplanar. And this one is the anti-periplanar. But don't worry about that. They're both periplanar. Everything's flat in the same plane. That's a requirement of E2. And if there's some weird structure that's preventing it from twisting, it might prevent the E2 reaction from happening. And that might lead to Zaitsel's rule being disobeyed, right? Zaitsel's rule says the alkene that has the most groups is supposed to be the major product. That's just a trend we see. We have to go back, and the E2 says, well, we have this extra rule, periplanar geometry. So there might be some cases where the molecule can't get into the right shape to give you the major product. So E2, you gotta watch out for. And I'm gonna limit it to chair conformations. I think the homework gives you another example of where periplanar geometry prevents Zaitsel's rule from working. But here's an example with a chair conformation, cyclohexane. The key idea is things have to be in the same plane. And to be in the same plane, the hydrogen and the halide must both be axial. You might have to build a model again of the chair conformation and convince yourself that all the equatorial bonds do not lie in the same plane. All the axial with equatorial pairs do not lie in the same plane. The only bonds that can lie in the same plane on adjacent carbons are the axial bonds. Okay, so how does this play out on an exam? Well, I might ask you to predict the product of this molecule with sodium hydroxide and base. I'm sorry, sodium hydroxide and water. Now, I picked these reagents today because we've already used those reagents. You've already identified them as likely for doing E2 reactions. On the exam, you might get a different set. The more practice we get, the better we'll get at identifying E2. Okay, for today, let's just look at these. I'll say, okay, predict the product here. And you'll say, okay, fine. These are E2 strong base, protic solvent, so no SN2, and strong base, good nucleophile. Sorry, that's a bad combination for SN2, no SN2. Strong bases, not SN1. We need weak bases there. Oh, sorry. Yeah, the nucleophile can't be a strong base. We said that for SN1. So right now this must be E2. And E2 says, well, wherever the halide is, begin your double bond. Go this way, remove the hydrogen. So maybe a double bond here. Or you could go this way and remove that hydrogen. Yeah, but we just said it's E2. So we have the extra requirement of periplanar geometry. So is this bromine in the same plane as this hydrogen? No. This bromine is equatorial. Both the hydrogen and the halide must be axial to be periplanar. So this hydrogen cannot react to that bromine because they're not in the same plane. They must both be axial. This hydrogen must be in the same plane as this bromine. They're not, because they're not both axial. So for this shape, there's no reaction. But we can do a chair flip. That's what the equilibrium is. And some of you just cringed. I know. Wait, chair flips was back in Unit 1. Aren't we done with that? chemistry. Chemistry is cumulative. It builds off of itself. So take that old concept, drawing the chair flip. So how do you do that? Well, make it wiggle. This is the low point down in a valley. So when it wiggles, the bromine will be on a high point up on the chair. Here's the foot of the chair, wiggles so that this is the head of the chair. It's going to go down here to be the foot. The foot of the chair wiggles, comes up to be the head. And then what was equatorial becomes axial. The bromine was slightly up, it's still up. Going clockwise, after the bromine comes a methyl equatorial. Well, after it goes the chair flip, what was equatorial comes axial. So clockwise, this equatorial bond went axial. Counterclockwise, hit the other methyl group over here. It was equatorial, now it's axial. Okay, so can sodium hydroxide do E2 on this? Well, the halide is axial, but the hydrogen's not. It's equatorial now. Hydrogen's equatorial. You still get no reaction. Darn it. What about this molecule? I've taken away the methyl group here. So we add base. Can we get E2 to happen? Here's the halide. There's two adjacent hydrogens, so maybe either one. Well, this one's axial, so that one has a shot. Ooh, but that's not axial. So there's no reaction here too. Remember, both halides and hydrogen must both be axial. So do a chair flip on this. Wiggle the foot to become the head. Wiggle the head to become the foot. Draw everything in the right place. Counterclockwise the methyl. Counterclockwise the methyl. Bromine, you're equatorial, now you're axial. Hydrogens, yeah, you're still both over there. Can this work now? Well, the bromine's axial, good. Ooh, no axial hydrogen on this side. Try this side. Yes, there is an axial hydrogen. So you can have one place to react. This base will pull off the axial hydrogen. These electrons will form a double bond here and kick out the bromine. So you get one product. The double bond is here. The axial bromine is gone. The axial hydrogen is gone. If you want to draw on the other hydrogen, it might, well, you could draw it like this. The problem is that this is sp2. So it should be flat here. There is a methyl going down over here. The hydrogen's still up. No change of this carbon. What if we look down on this? What would we see? Or in other words, let's get out of the chair conformation and draw just a normal skeletal drawing. So cyclohexane looks like that. Let's pick this carbon and this carbon to be this one and this one. So counterclockwise the methyl, and the methyl is down, so it's pointing down. What if we draw this one over here? So we got the hexane ring, right? I'll pick this carbon, that carbon to be this one and that one. So bromine is up. It's coming up towards us, and the methyl is down. What am I doing? I want to see if I had drawn this way, treated with base, what would I predict? If I had forgotten periplanar geometry and I said, oh, this is a secondary halide. There's a hydrogen here. There's a hydrogen here. Can't the base pull off this H and put the double bond here? And can't the base pull off this hydrogen and put the double bond here? I would have predicted two things. And which one's more stable? This alkene has 3 groups on it. I would have said this is the major product if I had forgotten to check for periplanar geometry. Down here, I did check for periplanar geometry. This hydrogen that hydrogen, they're the same. It's not periplanar. You cannot make this product. And now Zaitsel's rule was broken. Zaitsel's rule said, if you look at this structure, this should have been the major product. But in the lab, you don't even make that. This is your one and only product. Zaitsel's rule was broken. Be wary of the E2. On the exam, if you see it, I'm not saying you will or you won't, but if you do, it'll be in the context of a cyclohexane ring. So if you see cyclohexane show up, little red flag, think about periplanar geometry, which means you will have to draw the chair conformation and perhaps its chair flip. So homework will give you some practice with that. Ooh, are we done? We're done with the E2. Let's look at E1. Sn1. Okay, good news, bad news. Sn1, E1 go hand in hand. The 1 in Sn1 and E1, the 1 means unimolecular first order kinetics. For Sn1, the first step was forming the carbocation. For E1, same exact thing. The first step is forming the carbocation. If our reagent, well, let's just use water. No, let's not. Let's use methanol like we did before. I know, same solvent, same reagent, same starting material. You're gonna get both Sn1 and E1. It's a tie. They're both equally fast. It's not Sn2 because this is tertiary, and it's not E2 because that's not a strong base. This is neutral. Okay, so it's Sn1 because that's just a weak nucleophile. This is a weak base. It's also E1. So in the Sn1 mechanism, first step is form the carbocation. Then the nucleophile says, ooh, let's make a bond to that carbocation. And a second molecule of the nucleophile acts as a base to move that H. And you make an ether. An oxygen, 2 single bonds to carbon, plus the base form of the reagent. For E1, you're going to eliminate and form alkenes or alkynes. So you have the carbocation, and on the adjacent carbon, the weak base is going to remove a hydrogen, which would create the pi bond. And here's the only difference. Hey, lone pair, are you going after the carbon directly, or are you going after the adjacent hydrogen? If it attacks directly, that's a nucleophilic attack. Oxygen slightly negative, the carbon's full positive, opposites attract, that's nucleophile. This thing is seeking a nucleus and positive charge. Or turns out this hydrogen's slightly positive because carbon's positive. Being a positive ion, it's attracting these bonding electrons, which attract these bonding electrons, which creates a slight positive charge on that hydrogen. So the lone pair on oxygen, again, slightly negative, can say, well, plus carbon, or this one's easier, it's less crowded. Why don't you just grab that H instead? And then those bonding electrons will form the double bond, and you get an E2 reaction. So good news, bad news. Good news is, if you know the mechanism for Sn1, you're halfway through E1. It starts out exactly the same. Bad news is, if it's Sn1, it's probably also E1, so you need to draw both. We're going to get both this product and this product. I chose to remove a hydrogen off the top methyl group, but it could have been the other methyls to produce the same product. So I don't have to draw the other ones because it's the same product. Nice shortcut. What else do we need to know? The factors affecting E1 and Sn1 are practically identical. Again, that just means Sn1 and E1 are going to happen side by side. The 1 stands for unimolecular kinetics, same rate law as Sn1. Same rate law. Wait, that means the rates are the same? Yeah, they're both tied. Fastest rate wins. Sn1 and E1 are tied. And if you choose the structure, the shutdown Sn2, and you don't choose a strong base, shuts down E2. And Sn1 and E1 are the fastest, and they're going the same rate. It's a tie. There's no base in here, no nucleophile in the rate law, so it doesn't matter what you do with the other molecule. Changing that will have no effect on the rate. Same trend for E1 as Sn1, right? So they both make carbocations, so tertiary is the best, or the allylic or benzylic. It's opposite to Sn2, right? So what favors Sn1, E1 disfavors Sn2. And what favors Sn2? Primary. The primary carbocations don't work for Sn1, E1, so it shuts them down. Ew, carbocations can have rearranged products. So let's do this one. Okay, so what's the mechanism? Is it Sn2? Well, the halide says I'm secondary. It could be Sn2. What about the nucleophile? That's water. That's a weak base. Good nucleophiles are strong bases, and S, sulfur, and nitrogen. No, that's not a good nucleophile. This is probably not Sn2. Is it E2? No, this is a weak base. It's Sn1, E1. Yep. So let's form a carbocation. That's the first step for both. So let's take a shortcut. So it's both, put in parentheses, both Sn1 and E1. And the mechanism for both begins with making the carbocation. Then we got water. When I put that in here, the water is still present. So then what can then happen with that carbocation? Lots of things. Let's do the direct attack of water. First as a nucleophile, then as a base. Okay, nucleophile, attack the carbocation directly, attached to this carbon. Oxygen attaches in that step, carries along those 2 H's, it's making 3 bonds. Oxygen prefers 2, so another water molecule removes this hydrogen. Makes the alcohol and hydronium ion. We're done with the first one. There's one product. As a base, it can remove this hydrogen. Collapse to make the double bond. Double bonds there and hydronium. But you know what? It could have gone after this hydrogen. So adjacent to the carbocation are hydrogens either side. Double bond can go in either direction. Any cis-trans isomers with our alkenes? This one, no, that's neither cis nor trans. This one, ooh, the methyl, the identical groups are cis. Oh wait, the identical groups are also trans. There's a pair of methyls on this alkene. This one's neither cis nor trans. Awesome. Okay, so direct attack, taking care of all the possibilities of, let's see, this one was the Sn1. This one was an E1. You don't have to label this on the test, but I thought right now it might be helpful. Making alkenes is E1, substituting, where there used to be a bromine. Now there's an alcohol. That's substitution, Sn1. The other thing that can happen is right here, there's a tertiary carbon adjacent to a secondary carbocation. We can also get the hydride shift, a carbocation rearrangement. And again, you don't have to write this on the exam. You just have to show the products for it. Carbocation rearrangement. You don't have to write this. I am now, just to make it clear. The hydrogen goes down here so that the tertiary carbon then has 3 bonds. It lost the hydrogen, its 4th bond. So now the carbocation is right here and it's tertiary. Much more stable. Do all this again. To the carbocation that's now tertiary, maybe you get an Sn2 reaction. Sorry, Sn1. Sn1. Oxygen attacks the carbocation directly. This is going to need a water molecule to remove that extra hydrogen to go to the alcohol. The alcohol is now a tertiary alcohol. Over here, the alcohol is secondary. They're different. You have to draw both then. After the hydride shift, I'm going to leave the hydrogen out. You don't have to draw it in if you don't want to, because it's a skeletal drawing. Actually, put it back in there. Water molecule can attack that hydrogen. It's on the carbon adjacent to the carbocation. So the double bond could go there. You got your hydronium ion. And then the other thing is on the other side of the carbocation, either over here on this methyl or that methyl, they produce the same product. There's a hydrogen over there. I'm going to grab this one. The water molecule can go grab this hydrogen and do an E1 reaction. So this was E1 and that was E1. Yeah, I think you and I both are disliking the Sn1 and E1 because they go hand in hand usually. And if there's a carbocation that can rearrange, more products. Ooh, but that's all of them. I hope so. Okay, 4 factors. They parallel Sn1 for E1. So the base doesn't show up, just like it didn't show up in Sn1. That's what the 1 stands for, unimolecular. No base, no nucleophile in the rate law. So no effect. Leaving group, same for all of them, so it doesn't help the side. Solvent. Don't use one of the aprotic solvents, not one of the Sn2 solvents, because that'll speed up Sn2. Okay, and then protic solvents, I think we already listed this when we talked about Sn1. We need protic solvents because the aprotic ones will speed up Sn2. So the protic solvents are water, alcohol groups, like methanol we just used, ammonia, and the amines, right? That's a hydrogen. That's a nitrogen. So these are amines. You can use those as solvents, also as your base. This is a weak base, right? Amines from GenChem. Ammonia is a weak base from GenChem. They're also good nucleophiles. Good nucleophiles are strong bases, and Sn, ooh, the N stands for amine, nitrogen. Zaitsel's rule, still use it for E1. There is no periplanar geometry, yay! So if there's a chair, you don't have to draw it if it's an E1 mechanism, because you make a carbocation, you don't have periplanar geometry. Cool. Alrighty. So what we've done is gone over the remaining mechanisms, Sn1, E1, and E2. With the prior video on Sn2, we've seen all 4 factors for all 4 mechanisms. In our next video, because this one's getting too long, we'll break down how to decipher all that information. I like putting together a decision table. It's on Canvas, but it's right here too. I had a student draw it more neatly than I did. There's an alternate decision table on Canvas. See which one you like. But it's pretty straightforward. If you look at a reaction, first decide if the alkyl halide is primary, secondary, or tertiary. I like tertiary because that forbids the Sn2. It's too crowded. If it's tertiary, it doesn't do Sn2. It might do E2, it might do Sn1 and E1. How do you tell the difference? Decide if it's a strong base. That'll do E2. Bulkier is better. That's to stop the Sn2 from winning. Remember, Sn2 doesn't like crowding. So if your base gets crowded, E2 will be faster than Sn2. If you have a protic solvent and Sn1, E1 is favored. If it's not a strong base, it's favored. And if you use a solvent as your nucleophile base, that favors Sn1, E1. If it's a primary alkyl halide, that's going to shut down primary. That's going to shut down Sn1, E1, unless it's benzylic or allylic primary. All these exceptions. Sn2 is favored with primary. It'd be helpful if you use a protic solvent, one of the Sn2 solvents, DMF, DMSO, acetone, acetonitrile. And then lastly, secondary. You usually get a mixture of mechanisms working because secondary is a little crowded, but not too crowded to shut down Sn2. E2 doesn't care about secondary. Carbocations are secondary and doesn't work that well, but Sn2 didn't work that well. So we look at other things like the base or the nucleophile. If you have a good nucleophile, favors Sn2. If you have a weak base, that favors Sn1, E1. Strong base though, and secondary, that's going to favor E2, especially with a protic solvent. Alrighty, take a look at the homework. Help each other out in the discussion table. I'll try and get in the discussion post to help you guys out. And good luck. I'll see you in the next video.